Thank you. I would then like to introduce the next speaker, Johannes Louw, with his presentation is titled Text-to-Speech Generation Models for Resource-Scarce Languages in Neural Architectures.
Thank you. Can you see my screen?
Yes, we can.
Thank you. So I'm Aby Louw. I'm from the Voice Computing Research Group at the CSIR. And as was said, I'm talking about text-to-speech generation models for resource-scarce languages and neural architectures. So I'm just going to give a bit of a background on traditional speech synthesis pipelines, and then also compare that to end-to-end speech synthesis architectures. The goals of this work, the models that we used and compared in this work, our experiments, results, and a conclusion. So traditional text-to-speech architecture as a natural language processing block and a digital signal processing block. So input is a written target utterance, which is tokenized, normalized, part of speech tagging on the tokens, pause insertion, lexical lookup, and then phrasing is done. So all of that from the NLP block gives you a linguistic description that basically describes what the pronunciation of the target utterance will be, as well as its prosodic structures. Then you have your DSP block, which normally has a duration model, which determines the duration for each of your units, an intonation model, and then some other waveform generation, which then generates your synthesized speech waveform. So traditional TTS architectures require a lot of data. For example, commercial quality unit selection systems require more than 100 hours of data of a single speaker that has been recorded in a studio. They are generally difficult to train, and it's impossible to predict the quality. So sometimes it can sound really good, and sometimes there are there's some interference on the concatenation points of your units, and which may make it sound bad. Statistical parametric speech synthesis brought some improvements in terms of intelligibility, but it's not as natural as unit selection. So it's a lot smoother. You don't have the concatenation issues. And then DNN-based synthesis then again improves on the naturalness of the statistical parametric speech synthesis systems. And lastly, end-to-end systems, which are very close to human naturalness. So end-to-end speech synthesis architecture basically takes a character string as input, which does feature extraction, and then encodes that into a linguistic description. The linguistic description during training time is fed to the decoder, and spectral features used are normally also null spectrographs, like in Matthew's example. And these are then trained to give output to a vocoder, which synthesizes speech waveform. You have a attention block that aligns the linguistic description to the spectral features, which basically replaces a duration model from a traditional TTS architecture. So these systems have very close to human quality naturalness and intelligibility. And they've basically taken over most of TTS research. There's a challenge called the Blizzard Challenge, which runs annually, and participants get the same data, and then they must train a TTS voice. So 3-4 years ago, most of the systems were unit selection. In the last one, when this work was done, which was 2019, there was just one unit selection, and the rest were DNN and end-to-end and hybrid unit selection systems. So the success is basically attributed to the attention mechanism and the neural vocoders. And as an example of the data requirements and computational load, typical architecture is the Tachytron 2, which requires 40 hours of text and audio pairs. And then you get something like the DC-TTS, which requires about 10 hours. And the computational load is really heavy. For example, WaveGlow requires about, the NVIDIA one was 768 hours to train. It's fast on a graphics card, but it takes a long time to train. And these resources are usually not available for researchers in resource-scarce languages in terms of data as well as computational resources. So that brings us to the goal of this work, which is to develop a DNN-based speech synthesis architecture that can, at the very least, exceed the standard HMM-based approaches, which is generally used for resource-scarce languages. So the goal is to define an architecture with low computational costs, as well as very low or relatively low data requirements. So in our previous work that we presented at the FAIR 2019 conference, we focused on the vocoder and the acoustic model, where in this work we are focusing on the phonetic duration models. So I'm just going to explain the HMM. So we compared an HMM-based duration model to a DNN-based model. And I'm first going to explain the HMM model. So in our work, a fundamental unit of duration is a phoneme, and each phoneme is modeled as a 5-state left to right with no skip HMM. So in this figure, it's a 3-state if one excludes the emitting states. But this is just for ease of, we used a 5-state model. So during training, a decision tree-based context clustering technique is used to cluster the states of the HMMs. So these contexts are based on the linguistic context that is generated by the TTS front end, the NLP side. The clustered context dependent states are then tied and are re-estimated with embedded training, and then state duration probability density functions are also estimated during that training. They are Gaussian mixture models usually. During synthesis, the target text is converted to a context label by the TTS front end, and a sentence HMM is concatenated. After the concatenation, one can use the state duration PDFs to determine how many acoustic frames each of the HMM states must generate. So the DNN-based model that we defined in this work is a very simple feed-forward, fully connected feed-forward network with the output linear output layer, while the hidden layers were at the ReLU activation function. We had batch normalization and dropout with Adam optimization for the learning algorithm. And our loss function was the mean squared error on the predicted duration features. So during training, we fed the model, the linguistic descriptions generated by the TTS front end, and as well as our gold standard duration features, and then during synthesis, just the linguistic description, and then the network will predict the duration features. So in our experiments, we used an Afrikaans corpus of 56 minutes in duration, with 53 minutes of training data, about 2 minutes 40 of validation, and 10 utterances of duration 40 seconds for test. So all these durations were determined, which was our gold standard, was determined with HTK using a forced alignment technique. The objective measures that we used were the Pearson correlation coefficient to determine the linear correlation between each phoneme's duration. And the closer to 1, the better. And we also used the root mean square error in terms of the error number of frames per phone. In our results, we trained a few different architectures. HMM, we tried with our DNN different depths and different number of units in the hidden layers. We tried a few combinations. And as you can see, the best results were from on the test set were from 4 hidden layers with 128 units per layer. Yeah, so the correlation there was quite a lot higher than the standard HMM model, which was quite surprising. So in conclusion, we have defined an efficient and simple feed-forward neural network for speaker-dependent phonetic curation modeling in the context of resource-scarce text-to-speech settings. Our model trains in less than 2 hours on a CPU, and inference is faster than real-time on a CPU as well. We have also applied this model on isiXhosa, isiZulu, as well as Setswana, and we have had similar success. And we, I haven't got any MOS data here, but it was relatively high in comparison to our HMM system. So I've only got objective results here. For future work, we want to focus on data sharing techniques. So we think we might get away with more complex end-to-end, almost end-to-end techniques, but instead of using character-based inputs, we will use phonetic inputs and then share data between languages. So we start with a well-resourced language and try to go down to a resource-scarce language. And that's it. Thank you.